Alright, good morning, guys. I just want to give a couple quick reminders. Remember, our test is upcoming on Tuesday, so you will be getting your review on Monday. Just make sure you know about that. And then our Delta Math is due Sunday at midnight, so make sure you're completing those. Alright, I want you to take a moment, pause the video, and I want you to start with the warm-up question. Alright, now that you've unpaused the video, we're going to decide whether the events rely on each other or not. That means, is it independent versus is it dependent? So if I roll a dice and I flip a coin, do these two things rely on each other for their results? No, these are independent. If I'm pulling two marbles out of the bag without replacing the first one. So let's say I pull the first marble out and it's green. I do not put it back in the bag. And then I pull out a second marble and it's blue. Could I have pulled a green the second time if I had put the green back in? I could have, but I didn't replace it, so that means this is dependent. It relies on what you pulled first for your second options. Pulling 3 sodas from a cooler that only has Sprite. So if Sprite is my only option, it doesn't matter which ones I pull out, it only has Sprite. So this is independent. Eating 4 pieces of chocolate from a Valentine's chocolate box. So I'm not sure if you've ever had those little heart ones that have like little pieces of candy in them. And they're all different types. Let's say I eat the orange one first. I can no longer pick an orange one. So then my next option depends on what I chose first. So these are just a gist on what is independent, means they do not rely on each other, versus dependent, they do rely on each other. So go ahead and get out your notes packet. We are going to be talking about the multiplication rule today. So number 1, suppose we have a set of 40 cards consisting of 10 blue cards labeled 1 through 10, 10 green cards labeled 1 through 10, 10 red cards labeled 1 through 10, and 10 yellow cards labeled 1 through 10. So to summarize, this table is what we have. A card will be selected at random. If it is an 8, 9, or 10, you will win a prize. So I'm going to go and I'm going to highlight my options. If it's an 8, if it's a 9, or if it's a 10, I will get a prize. So what is the probability that you will win a prize? So we have 40 cards total, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of those cards would allow me to get a prize. So 12 out of 40. But we also need to add our probability notation. So the probability that we get a prize is 12 out of 20. But this fraction can reduce, so we're going to reduce it to 3 out of 10, and then convert it to a decimal, which is 0.3. So we have a 3.3 chance to win a prize. Now, suppose someone selects the card for you and tells you that the card is blue. Okay, the card is blue. But doesn't tell you what the number is on the card. Does this change the probability that you will win the prize? So, remember, this is telling us that it's conditional. We are given that it is a blue card, but we don't know what number it is. Okay, so we are going to take our data and we're going to narrow it down to just blue. Okay, so we're going to be dividing by the blue cards. But we still want to win the prize. So we want the prizes over the blue cards. So how many prizes could I win if I chose blue? 3. And then how many blue cards are there? 10. So 3 out of 10, which is 0.3 as a decimal. So does this change the probability that we will win a prize? No, because it's the same as above. Okay. So part C, using probability notation, the probability you found in part A is written as P prize. How would you use probability notation to write probability in part B? Well, I already started it right here because we said we were given B. So let's go ahead and finish that. Probability, we want to win a prize, but we are given that the card is blue. All right, do you have any questions about number 1? If so, let me know. Write them down, send me an email. Now, the fact that the probability of a prize given blue and probability of a prize are equal, that tells us the events of winning a prize and picking a blue card are independent. Okay, they're independent. Knowing that the card is blue does not change the probability you will win a prize. If 2 events are independent, the following is true. If the probability of A given B equals the probability of A, and the probability of B given A equals the probability of B, the 2 events are independent. So we will use this relationship to determine if 2 events are independent. Now we're going to take a detour for a moment, and we're just going to talk about independent and dependent events. So the definition of independent is they are not affected. So the second event is not affected by the first. Some examples: you can spin a spinner with 4 equal sections, numbered 1 through 4, and toss a coin. You could spin a 4 and toss heads. Those do not rely on each other for their outcome. You could roll a 6-sided dice, numbered 1 through 6. You could roll a 2 on the first roll, and you could roll a 5 on the second roll. What you roll first does not determine what you roll next, because it's the same dice, it could land on the same number. Now, dependent events. 2 events are dependent if the result of the second is affected. So this time it is affected by the first. So if I pick 2 marbles out of a bowl and do not replace the first marble before drawing the second one. So this is like that warm-up question where I said if I pull out a green first and I don't put it back in, and then I pull out a blue, those are dependent because if I put the green back in, I could have also drawn it again. But when it's not there, I can't do it. Choosing 2 different names out of a hat to win first place and second place. If I pull a name for first place, I can't pull the same name for second place. All right, let's do another example together. Number 2, suppose that you roll a cube with faces numbered 1 through 6. Let E be the event that the cube shows an even number. So E for even number. Let F be the event that the cube shows greater than 2. And let G be the event it shows greater than 3. So let's find the probability of E. So it just says we're rolling a cube numbered 1 through 6. So I'm going to list out all my options. And E says we want an even number. So 2, 4, and 6. So the probability for E, we have 3 options that are even divided by 6 total, which is 1/2, which is 0.5. Find the probability of E given F. Okay, so we're going to list out our numbers again, 1 through 6. Now, we are given F, so we have to deal with F first. F says it's greater than 2, which means we cannot use 1 and we cannot use 2. So, how many of these options are even? We have 4 and we have 6. So the probability of E given F, there are 2 options, but we don't have 6 total options anymore. Remember, the given part F is what is our denominator. So now we are only left with 4 options. So that's still equal to 1/2, which is 0.5. So the second part of this question says, are they independent? So we're going to go back to page 1 real quick. It says, 2 events are independent if the probability of A given B is equal to the probability of A. So, is the probability of E given F equal to the probability of E? So is 0.5 equal to 0.5? The answer is yes, these are independent. So now I want you to pause the video and try letter C. Alright, now that you're done with letter C, we are going to write out our sample space. 1, 2, 3, 4, 5, 6. We want the probability of E given G. So G says greater than 3. So I'm going to eliminate 1 through 3 because those are not part of G. Then we want to know how many are even. So 4 and 6. So probability of E given G. There are 2 options that are even, and G leaves us with 3 options total, which gives us a decimal of 0.66. So to find out if they are independent, we do probability of E given G, and we want to know, is it equal to the probability of E? So does 0.66 equal 0.5? The answer is no, they are not equal. So they are not independent. Alright, sometimes you are only given the probabilities and you would like to determine the events that are if they are independent or not. Based on the situation, you might think that the events are dependent. You need to do an analysis of the data to be sure. So far we've just been working with simple stuff, but we do need to work with some tree diagrams. So let the event that it is sunny tomorrow be S. Okay, so S means sunny. Let the event that Emily will go jogging be J. So jogging is J. The probabilities are shown. So find the probability of J. Now, we didn't quite get to this on tree diagram day. We didn't do the practices that showed us how to do this. So to find the probability of J, you are going to take your 2 pathways. So pathway 1 and pathway 2. To find the probability of J, you're going to take pathway 1, so the 0.7, and you're going to multiply it by 0.8. So you're going to multiply these two branches together. But then we also have to add multiplying these two branches together for that s complement. So 0.3 times 0.8. So now this is where we plug them into the calculator. So the probability of J is 0.56 plus 0.24, which adds up to 0.8. Now, you're probably wondering why this is different than what we did the other day. When we're trying to find the probability of J, we have two situations that have J. So we have to take both of those into account. But also, the second branch depends on the first branch, if it's sunny or if it's not sunny. Now, part B, find the probability of J given S. Now, this one is exactly how we did it the other day. When we are given S, we are just looking at this second part. So S is our pathway, but we are only looking at J. So the probability of J given S is 0.8. So are J and S independent? To find that out, we do probability of J given S, and it has to equal the probability of J. So does 0.8 equal 0.8? The answer is yes. All right. Now, find the probability of J given S complement. Remember, complement means not S. So the probability of J given S complement, we're going to follow the pathway for S complement, but we only want this J part. We only want that branch. So that's 0.8. So now we want to determine if they're independent. So P, probability of J given S complement, must equal the probability of J. So does 0.8 equal 0.8? The answer is yes, they are independent. All right, if you have any questions, make sure you're writing them down, asking me, sending me an email. So now, based on what we did in number 3, I want you to pause the video and do number 4. All right, hopefully you've already done number 4. You'll be able to check the key to see if your answers are correct later on in the day when it is posted. But we're going to go to the last page, okay? Not the last page of the packet, just the next page. So in the first part of this lesson, we showed you that two independent events, the probability of A given B, equals the probability of A. The other day, though, on conditional day, we taught you that the probability of A given B is the probability of A and B divided by the probability of B. So if we take what we know from conditional and substitute it in for the probability of A given B, we end up with this formula right here. But we could do some algebra so we don't have a fraction, and we can multiply both sides of the equation by the probability of b. That gives us this equation. The probability of a and b equals the probability of a times the probability of b. So, the events a and b are independent if and only if the probability of a and b equals the probability of a times the probability of b. This is what you were introduced to on the Skittles lab day. So, here's some information about houses on Hector Street. The probability of G is 0.25, probability of F is 0.76, and the probability of P and G is 0.19. Use the formula above to show G and F are independent events. So the formula is the probability of G and F equals the probability of G times the probability of F. So the probability of G and F is 0.19, and that has to equal the probability of G is 0.25 times the probability of F is 0.76. So take a moment, plug that in your calculator. You should get 0.19. So does 0.19 equal 0.19? Yes, so they are independent. All right. Number 6. Suppose that you will flip a coin and that you will roll a cube with faces numbered 1 through, should say 6. There should be a 6 here. What is the probability that the coin will land heads up and the cube will show a 6? So if we're using that formula above, the probability, it said we want to land on heads and we want to show a 6. That's equal to the probability of landing on heads times the probability of landing on a 6. So the probability of landing on heads, you have 1 out of 2 options because we have heads or tails. And for a cube with a 6, you have 1 out of 6 options. So I can multiply these. I get 1 over 12, which is 0.083. So I have a 0.083 probability that I will land heads up and the cube will show a 6. All right, if you have any questions, make sure you're writing them down, getting ready to ask me or emailing me. You are now responsible for questions 7, 8, and 9. Okay, so you should have already done number 4, but now you are responsible for 7, 8, and 9. You can check the key later to see if your answers are correct. Once you finish this, there's a quizzes posted on that Google Classroom post. If you finish that, you can work on your Delta Math. If you finish everything, make sure you have all your missing assignments done for me. Remember, everything is due next week. If you have any questions, email me. Have a great day.